Welcome back to our course on scanning electron ion probe microscopy in material characterization. We have been discussing on scanning probe microscopy. In that topic, we are now covering the atomic force microscope. In our last lecture, I discussed different modes of AFM operation, and today I will be discussing with some examples of AFM images taken in different modes. We have discussed on these three different modes. One is contact mode AFM, non-contact mode AFM, and then intermittent contact mode or tapping mode. So, the contact mode operates when the tip and sample are in contact with each other. So, the distance between tip and sample is very small in the contact mode. It is about less than 0.5 nanometer. So, in the contact mode, our gap between the sample and tip is less than 0.5 nanometer, and this is the region where repulsive force dominates or predominates, and this contact mode can give high resolution AFM image. However, there are also demerits. The contact mode operation put a force of approximately 1 nanonewton to 10 nanonewton or maybe even more up to 100 nanonewton, and that much of force can create plastic deformation on the sample surface. So, the plastic deformation occurs because with that force it will create a pressure in of few gigapascal, which is almost in the same order as that of yield strength or yield stress, and thus causing deformation to the sample, mostly for soft sample, polymeric sample. This happens with contact mode. And also another point with contact mode is that when tip is in contact with the surface of the sample, then there will be shear force. There will be lateral moments of the tip, creating the shear force or lateral force, horizontal motion of the tip. We will see more detail onto the lateral force microscopy. In addition to that, there will be capillary force that will play into the role. So, all those type of force which are short range in order, they will come in into picture when we do contact mode of AFM operation. But in the non-contact mode of operation, we have distance between some tip and sample is little far, and it is greater than 2 nanometer, and in the intermediate contact mode, the separation between tip and sample is in the range of around 0.5 nanometer to 2 nanometer. So, in the non-contact mode, now tip goes much away from the sample surface, and therefore, it cannot damage the sample, and non-contact mode mostly operated in a dynamic mode. That means, tip is oscillated, probe is oscillated above the sample surface, and then we measure the frequency shift or the change in the oscillations of the cantilever and tip. Now, in the non-contact mode, first of all, the resolution will be not as good as that of contact mode, but the main problem is that we cannot if we want to operate in the ambient condition. At the ambient condition, there will be always a water layers on the sample surface. So, as water layer or a fluid layer covered the sample surface in the ambient condition, the force that we will measure by the tip is not the actual force between the sample and the tip, but rather the water layer and the tip. So, the water layer marks the actual sample surface properties in the non-contact mode of AFM operation. So, in order to avoid that, one has to do one can do the non-contact mode either in vacuum and then there will be no water vapors on the surface of the sample or in the dry condition. Similarly, one of the problems with the contact mode was the capillary force. In the contact mode, capillary force come into picture. So, capillary force will also play or impact the force measurement. In addition to that, shear force will also act here. So, these things in the contact mode can also be avoided by doing the experiments in a certain medium such as under liquid. So, under the liquid there will be no capillary force, and therefore, that capillary force can be avoided in the contact mode. And then the non-contact mode, in case of non-contact mode, certainly force will be less. It is the force will be less than 1 nanonewton. Here in contact mode it is greater than 1 nanonewton. In the intermediate contact mode, the tips come periodically and touch the sample. So, it takes the advantage of both contact mode and non-contact mode, thereby it will not damage the surface, and here also the force will be much smaller. Certainly, force will be less than 1 nanonewton, and the duration for which it will come in touch is 2 orders of magnitude less than that in contact mode, and thus it will not damage the sample unless this tapping is very hard. If the tapping or this that is why the hard impact is happening, unless the hard impact is happening, the chances of forming damage in the tapping mode is also less. And also, as in these cases in the tapping mode, sample is coming and periodically going to touch the sample, the other forces such as water vapor layer, liquid layer on the surface will also can be avoided, its effects can be avoided. So, these are the 3 different modes we use in atomic force microscopy, but most commonly we use intermittent contact or tapping mode of operation for all kind of sample. For organic and polymeric sample, contact mode is not at all prepared, but for hard sample or for when we look for high resolution imaging, then contact mode can be used. Similarly, non-contact mode is prepared for the sample like polymer sample, organic sample, where there is a chances of damaging the sample is concerned, we can use the non-contact mode. So, these 3 modes are primarily operated in the atomic force microscopic study. If we look at the properties of these different modes, certainly the tip loading force with a contact mode is normally high compared to other. It is normally as I have mentioned more than 1 nanonewton. In non-contact and tapping mode, loading force, that is the force we load on the cantilever tip, is less. Similarly, contact with the sample, contact mode yes, non-contact mode no, and tapping mode periodical. Contamination, as in contact mode, tip is in touch with the sample, and certainly contamination will occur to the sample. Non-contact mode, there will be no contamination and the tip can last longer, and also the contaminants on the tip will not influence the imaging purpose. In tapping mode, again contamination probability is there. Manipulation of the sample, contact mode we can do manipulation, non-contact mode we cannot do manipulation, tapping mode we can do manipulation. Manipulation can only be done when the tip come in contact with the sample surface. As per the force of interaction is concerned, in the contact mode we use a small spring constant value that will allow us for high sensitive force gradient measurements, thereby giving us high resolution. In the dynamic mode, as the probe has to oscillate, therefore, we have to have higher resonance frequency, and in order to as the resonance frequency requirement of resonance frequency is there in the tapping mode, automatically resonance frequency is directly proportional to the force constant or spring constant, therefore, the tapping mode spring constant is automatically greater. So, there are two type of interaction force, that is repulsive interaction, attractive interaction. In the attractive contact mode, we will certainly have a repulsive interaction as tip comes close to the sample. So, repulsive interaction, but in the non contact mode there will be attractive interaction, and its again the force is less, and in the dynamic mode the measurements can be or detection can be amplitude modulation or frequency modulation. This can be done and with a high spring constant value. This is an example how contact mode gives high resolution imaging, atomic resolution. As you see in the left side, that you see is a AFM image of exfoliated black phosphorus on a silicon oxide substrates in a operated in the ambient condition with a humidity, certain humidity and temperature at 18 degree centigrade. It gives the crystal structure. The lattice planes can be visualized, and the distance between two lattice plane is measured to be around 4.3 angstrom here. And this right side scale, as you see this scale, this brightness contrast scale is from this image, where there is a higher brightness that is above the sample, that is close to the tip, and where most darkest place or darker contrast is there, that is here, which is at the bottom of the sample, or which is most deepest part of the sample. So, by measuring this brightness contrast, we can know how much the most lowest part in the sample surface or deepest part in the sample surface, and the most the tallest parts in the sample surface, the bottom height and top height. This is the top height, is the brightness brighter, and this is the darker portion in the image. The sample can be rough. So, which is the bottommost part is the dark contrast, and which is the topmost parts of the sample, which is appeared as a brighter portion. So, now as we see here that this varies from 0 to 1.5 angstrom. That means, most brightest region is just 1 angstrom above the 1 angstrom above the most darkest part, or the maximum height in this sample is 1.5 angstrom. So, we are able to measure the thickness of the sample in the angstrom region, 1.5 angstrom. And the right side, there is you see another example of atomically resolved potassium bromide. Here this brighter, this part is our bromine atom, which is a bigger size, and other part, this part is the potassium position, and we can measure the distance between two potassium atoms, 0.66 nanometer in these cases, and also we can measure the diameter of the bromine ion using the atomic force microscope in the contact mode. So, here why we see the brighter here is because our tip is more close to the sample surface. As tip is much closer to the sample surface, there is a positive force of gradient because of the repulsion. We in the tip of the cantilever or AFM tip, we have atoms, and they have atoms have electron clouds. Those electron clouds, when come in contact with the electron clouds of the atom in the sample, there will be repulsion, that is called Pauli repulsion, and that repulsion leads to the higher force gradient, and we are measuring the force gradient. Therefore, it looks much brighter, but in other places it is less brighter because the electron clouds of the potassium atom and the tip atom do not overlap much. So, there is no, and therefore, it is less brighter, and in other places where there is nothing is there is no repulsion is occurring, because the contact mode operates in the repulsive regime of the Lennard curves. So, therefore, where there is nothing, no atoms is present, there will be no repulsion, that is therefore, we do not see any brighter, there is no repulsion, there is no repulsive force, and therefore, it looks darker. So, this is what the contact mode image presents to us, giving us the lattice constants, distance between atoms, distance between atomic planes, all these can be measured in the contact mode of AFM operation. If we look at the non-contact mode of AFM image, as I mentioned, this is used for organic sample and polymeric sample. In this mode, tip is much away from the sample, but still it in the modern day AFM, up to due to the several developments, the non-contact mode atomic force microscope can also produce quite atomically resolved images that you see here. In this particular cases, organic molecule is taken, that is 1,2-bis ethylene methyl phenyl benzene. These organic molecules is thermally activated at different temperature, and it was found that when temperature is given more than 90 degree, this reactant is converted to 3 different products, and those products can be seen by atomic force microscopy in non-contact mode. What you see in the left side, this is this organic molecule, and as you see there are 3 6-membered ring, and if you look at this AFM image, you see the 6-membered ring, which is the brighter portion. The dark halo around this brighter portion is, there is no atoms or nothing is there, that portion darker is due to the electrostatic force of attraction. Those portions are the electrostatic force of attraction, this darker region, but the brighter region are due to the repulsion of atoms in the organic molecules and the atoms at the AFM tip. So, those repulsion giving the brighter contrast, we could see wherever the electron cloud is there, it is more brighter, where it is more brighter at the region where corners are there, where atoms are present, carbon atoms are present, and then also because it forms the bond, there is electron clouds overlap, and therefore, in the bond region also we could see the brighter contrast, and it clearly shows here, as you see also here a triple bond, we could see a brighter contrast here. Similarly, this is the scale of 3 angstrom, this is a lateral scale, we could measure the distance between the bond, distance between the atoms. At the same time, in the bottom, this scale is the frequency shift scale. This as you remember, our dynamic mode of operation involves frequency modulation detection or amplitude modulation detection. For the non-contact mode, we prefer frequency modulation detection, but for tapping mode, we prefer amplitude modulation detection. So, this photo images is taken through a frequency shift and constant height mode. It was placed, the tip was oscillated above the sample with a constant height with a particular resonance frequency, and the frequency shift due to different force of attraction is measured. As the frequency shift is more positive, that means more brighter. Frequency shift more positive means there is more repulsion, and frequency shift is more negative means there is attractive force. So, the darker part of these photographs is due to attractive force, which makes the frequency to shift to negative direction. If you remember correctly, that is what I mentioned in our last lecture. Frequency shifts in the negative direction is due to the attractive force. Attractive force in this region is due to electrostatic force of attraction or van der Waals forces, but here the brighter part is due to the repulsive force. And in all these 3 cases, the 3 different products can be, these are the AFM image and the corresponding the schematic of the organic molecules is given in the bottom parts. You see they are quite well matched, and our AFM image is able to provide us the 4-member, 5-member, 6-member ring of the organic molecule. So, this is what the capability of non-contact mode in present day atomic force microscope. And if we go for tapping mode, certainly tapping mode is much closer to the contact mode, and therefore, tapping mode can also provide us the atomic resolution image. So, here is an example of with a silicon surface, silicon 111 surface with a 7 into 7 reconstruction surface, and here comparison is done with STM. This A1, A is the image A is the atomic force microscope image. We can see the atoms where the bright dots are there, those are atoms, and where there is darker portion, there is nothing is there. So, as you can see in this image how these atoms are arranged on the surface of a sample, surface of the silicon wafer here, and this line is called line scan. If we put a line on the photographs, it gives the intensity variation, that means brighter and darker contrast variation. If we notice it and you see this, the scale bar is 2 angstrom. The bottom part of this photograph, the darkest part is here and the highest part is here. So, this gap is almost like 1 angstrom. We could see that how much the height of a particular atom by atomic force microscope in the tapping mode. And if we look, this is the atomic force microscope image, and in comparison, and this is the B is our STM image of the same surface recorded with a by applying a negative bias to the tip. If we apply a negative bias to the tip, minus 2 volt is applied to the tip, it will give the empty states of the sample, because electrons will now flow from the filled states of the tip to the empty states of the sample. That is why it is giving the empty states of the surface of silicon. Now, the atoms which have empty states available, they will receive the electron from the tip, because we are applying a negative bias to the tip. That is, we are imaging the empty states atom of the surface using the STM that we have discussed before. Similarly, the right one, the same surface, but here tip is applied with a positive bias. As tip is applied with a positive bias, electrons will go from the filled state of sample to the empty states of the tip. So, as it happens like that in opposite way, so we see the atoms on the silicon surface which are filled states. So, the electronic structure or density of states measurements is performed with STM. That is what we have already been discussed. The density of states measurements can be done by scanning tunneling microscope, because we measure the current. So, by measuring the current, which direction it is flowing and how much current is flowing, we could also know the positioning of the atoms, distance between atoms, and also the height. So, all this information can be obtained, and in the STM image was recorded with a constant current mode. So, it measures, we can do constant height mode and constant current mode, 2 modes we can use in STM, and this was done with a constant current mode. By this, we can again see here tapping mode giving us atomic resolution image of the sample surface using atomic force microscope and certainly STM. But if we compare the lateral resolution is concerned, the STM is much superior to the AFM lateral resolution, because here we are measuring the tunneling current in the nanoampere region, nanoampere range, providing us a clear view of each atoms on the sample surface. Certainly, atomic force microscope is very frequently used for measuring the thickness of the 2-dimensional material. So, here in example that you see the thickness of a monolayer of nanosheets, like we in the present day a lot of research is going on 2D materials, and AFM is the most suitable and most appropriate technique to measure the thickness of monolayer or thickness of any type of nanosheets, nanoplates, etc. And in these cases, that is what been presented or shown here. Then there are hexagonal sheets of indium selenides nanosheets. They are with different thickness, and in the right, this is the line scan giving us the thickness of the nanosheets. because tip gauge, as soon as it see an objects or 2D materials, tip gauge up and then scan, then gauge down. In this way, tip gauge, and when you see the surface, we can measure the thickness here. So, this is what the line scan is providing, and there are several nanosheets here, several nanosheets also presenting the thickness, whether they are stacked over each other and what is their thickness, whether there is individual nanosheets or there are multiple nanosheets are there. That is what we are measuring here. Another more important information that we do get in the atomic force microscope is the phase imaging. So, phase imaging is particularly done for the sample which are inhomogeneous in nature, and thereby getting the phase shift. For example, phase image, it is a secondary mode of imaging in a derived from either tapping mode or non-contact mode. In the tapping mode, tip oscillates on the surface. Similarly, in the non-contact mode, tip oscillate on the surface, that is dynamic mode. In the dynamic mode of operation, when our cantilever probe is oscillating above the surface, it is oscillating with it at its resonance frequency. So, now as the oscillation occurs on the surface of the sample of different nature, that is what you see here. Here is, let us say, here is a one type of sample and there is another type of sample, but sample is smooth. As per the surface is concerned, there is featureless, everywhere flat, but one place there is one kind of sample, there is given in different colors than to the regular sample. Now, when the tip gauge of it keep on oscillating with a particular resonance frequency, one type of phase shift occurs here. The phase shift value here is 1, and another phase shift value. Phase shift will not be same when it goes to another kind of material. So, phase shift will be different. So, we can measure that phase shift, and that phase shift can tell us about the variation of the composition, adhesion, friction, viscoelasticity and other properties, including electric and magnetic properties. Even though the surface is smooth, there is nothing is there. Let us say on this surface, the surface is completely flat, but there are some chemicals attached to the surface. Now, because of this chemical presence of this chemical, the tip oscillation will vary. Not only its amplitude may vary, but also the phase shift will occur. And by measuring that phase shift, we can know whether there is a inhomogeneity is there. So, in this phase imaging cases, AFM operates as usually by detecting the change of cantilever oscillation. Cantilever oscillation, that is either may be frequency mode detection or amplitude mode detection. We will certainly know the surface roughness, no doubt, when the tip is going above. But in addition to, so oscillation, one is amplitude will change when the sample come close to the tip, then damping of the oscillation occurs, amplitude reduces as we discussed in the tapping mode. So, when the distance between tip sample is less, then there will be decrease in the amplitude, but when distance between tip and sample are far, there will be oscillation, amplitude will be more. So, that is used to create the topography, but in addition to the amplitude changes, there are also change in the phase of the oscillation, and that phase is used for phase measurement. So, in addition to mapping the topography, it also may measure the phase of the cantilever periodic oscillation relative to the phase of the periodic oscillation that drives the cantilever. So, we give a driver signal, one particular signal that we give with a particular phase value, and now in the detector we will notice how much phase shift occurs. So, by knowing if there is a non-uniform phase shift, that indicates that there is two different kind of materials. So, more of this phase imaging we will discuss in our next lecture. So, what I have discussed today in this lecture is that there is contact mode and tapping mode, both are routinely used for achieving the atomic resolution image, but non-contact mode is used for organic molecules, polymeric molecules to get molecular structure, etc. We cannot use contact mode or tapping mode because we have more chance to damage the sample surface. Moreover, non-contact mode has a disadvantages that true surface information may not be obtained or will not be obtained unless it is done in ultra high vacuum condition. What the examples I have presented was done in ultra high vacuum condition, not in the ambient condition. So, as there was no ambient in presence of ambient condition or in ambient condition, there will be a water layer, we actually would not able to see the organic chemicals on the surface of surface. And phase imaging that we briefly introduced is used to get additional surface information which cannot be obtained from the topography data. So, I will give example of phase imaging in our next lecture, and also we will discuss some of that effects. So, then we see the reference here, reference book, and thank you.